Hello and welcome to this episode where we're going to make a deep dive into the modular building blocks, electronic building blocks, and we're going to look at the OpAmp Comparator, which is one of many building blocks that is reoccurring in the schematics all the time. And the reason I want to take this up is because when I figured out how this worked, I had an aha moment or an epiphany about why it is and how it can be used and how it's solved quite a lot of my problems and thoughts I've had about a few modules. And it's a really versatile module, especially when working with gates, which I'll go into in a moment. While we're looking at the OpAmp Comparator, I will also talk a bit about the voltage divider, which is another electronic building block used very many times. All the knobs is almost always a voltage divider. But it is also one part of the OpAmp Comparator. I'm not going to go into detail of the mathematics behind it and how it works in theory. I just want to show you how it works in practice, because that's the important part of in my case, and that's what I can show. If you need to, if you want to know the theory behind it, there are loads of other YouTube videos to watch that. But what an OpAmp comparator is, it is, as the name implies, it compares the two inputs, the inverted input and the non-inverted input. It compares these two, and on one of the inputs you have a threshold value, let's call it that, which you set with a voltage divider. And when the other input, and when you compare that to the threshold value, if it is below that threshold value, then the output of that OpAmp will be negative voltage. If you have a plus minus OpAmp, it will be negative voltage. If it is above the threshold value, it will be positive voltage. So you will technically take a analog voltage and do that into binary. Either it's on or off, or minus or plus. For example, if you want a gate and you don't know what gate values you want to have, because some modular modules have 5 volt gates, some have
6 volts, some have 8 volts, and some have 10 and 12.
There's a large variety of gate voltages, and some are below 5 as well. And if you listen to many discussions and read online, you will know that not all modules can handle all gate signals. With the OpAmp Comparator, which I will make a module in the next video that takes a gate signal. So we take a voltage divider to 1 volt, so anything above 1 volt will become a gated signal, and it can be 1 volt all the way up to 12 volts. So that's the magic of the OpAmp Comparator. And then you can of course have a potentiometer for the voltage divider and decide what value you want for when the gate should be on or off. So very interesting building block. So let's go and look on how the schematics looks like and how we can build this into a useful part of a modular module. And before doing that, I would also like to say thank you to my Patreons who support me over at Patreon and make these videos a bit easier for me to make. And with that said, let's go and look at the schematics. This is a really good picture of the OpAmp Comparator. So down here you see on the inverting input, you have the voltage reference input, and then you have the non-inverting input, you have the voltage input of whatever signal you want to compare to the reference signal. And when voltage in is higher than voltage reference, then V out is equal to voltage plus. And if it's lower than voltage reference, then voltage out is voltage minus. And that is how this would look when you raise the voltage input. So when it goes over the threshold, it goes from negative voltage to positive voltage. Here is a common example used in many synth designs and modular modules. So first we have a voltage divider here with 10k to ground and 100k to voltage plus, which in this case gives us around 1 voltage. Reference voltage is 1 volt. And then we have the input, so when this one is lower than 1 volt, we get minus voltage on the output, and when it is higher than 1 volt, we get plus voltage on the output. And this is a common thing to add a 1N4148 or diode to make the signal either plus voltage or ground, so we're not down in the negative voltage, because we're working with gates in this example. There are loads of voltage divider calculators out there, so if you need to find out what resistors to use for your voltage divider, then just go online and do a search for voltage divider calculator, and you will find loads of different sites offering this service. I really like this one from ohmslawcalculator.com/voltage-divider-calculator, because you can just add any 3 values, known values, and get the 4th one out from this. So if we, for example, add 12 volts here as our voltage source, we have 100k as our resistor towards voltage plus, and we want 1 voltage out. And when we press calculate, we get that the exact resistance value of R2 towards ground should be 9090.909 ohms for us to get a voltage of 1 volt. But if we instead write the closest value to 1990, so 10,000 ohms or 10k, then we instead do a new calculation, remove the voltage output, we get that with those 2 values we get 1.091 volts output, which I believe is close enough to 1 volt for this example. Let's look at 2 of the schematics from the last Modular in a Week episode where we did the clock dividers. So here's the clock input of the CV2 clock divider that we did in that episode, and here we have the clock input coming in on the positive input of this OpAmp. There is a feedback with really high resistance, 2.2 plus 2.2 mega ohms, so 4.4, really high resistance there. And there's also a 100k to ground. Now, the interesting thing is that the negative input is connected here to a voltage divider. So this is connected with a 100k to voltage plus, 12 volts in this case, and a 15k to ground. So, and this means that the input of the negative input is around between 1 and 2 volts. So if the clock input is lower than, say, 2 volts, then the output is minus 12 volts, because we run the TL072 in this case from plus 12 volts and minus 12 volts. So when the clock is lower than the input voltage reference, the output is minus 12 volts. If the clock is higher than 2 volts, then the output is plus 12 volts. That's how easy it is. So it just goes up to 2 volts, and as soon as it goes over, the comparator circuitry changes it from minus 12 volts to plus 12 volts. And then we have a diode afterwards, because we don't want the negative voltage into the 4024 or an Arduino or anything like that. There is also a 100k resistor to ground after the diode. Another one, very similar, but completely different schematics, but the OpAmp comparator is very similar. So here we have the clock input on the positive input of the OpAmp. It is powered by a minus 12 volts and plus 12 volts. The negative input is connected to a voltage divider with 10k to ground and 100k to 12 volts. And this gives the voltage reference to around 1 volt. So if the clock input is lower than 1 volt, we have minus 12 volts out. And if it is higher than the voltage reference, then we have plus 12 volts out. Again, a diode. So here I've hooked up a simple OpAmp comparator according to the schematics that I link in the description and that you can see on screen right now. It is connected to a plus minus 12 volt power supply that I walked through and built a couple of videos ago. And let's make some measurements here. Let's begin with the voltage divider. So here we have ground and plus 12 volts. Then we have the voltage reference input, and there we have added a voltage divider with these two resistors. So this pin 2 should read 1 volt, and that is because we have 100k to voltage plus and 10k to ground. That ends up at 1 volt. And that means that we have nothing on the input right now, so the output should technically be minus 12 volts. It is in fact 0 because we have a diode here. But if we remove that one and just check the voltage on the output pin of the OpAmp comparator, it is minus 10.68, so about minus 12 volts. But because we add a diode here, the output signal is kind of 0. It is not exactly 0, and that is why we add this extra resistor, 100k resistor to ground, and now we get absolute 0. Now let's add some kind of voltage to the input, and let's see what happens to the output. So we've added a few components to this circuitry. This is a scalar and bias circuit that I will go through some other time. I did this in the AAC VCO. This is part of that circuit, but it is also very nice to have it as its own circuit, because when you want to inject some CV into something and want to slowly scale it up, it's very nice. I'm also taking 5 volts from the bare boards Arduino we built also a couple of episodes ago, the Jan Ostman one. So right now it's just for the 5 volts. And as you can see, we are still at 0 volts on the, and still measuring the output. So if we slowly take the voltage up here, we should see there it went up to 10.93, so almost 12 volts there. So let's remove this and let's measure the output here of the from the scaler and see how much voltage that is. So that is 1.36 volts, and that's what made this circuitry go up to 10 volts. And this means that you can take, why this is a really good circuit, and why I want to show you this, is because this one you can use in so many projects where you have a fluctuating voltage or you don't know the exact voltage, and this one will make the output exact. Now you might need to lower this voltage again by adding a resistor of some kind, but you get an exact value of the output no matter what the input is. So that is a really good use of the OpAmp comparator. And with this new knowledge and this building block, I hope you have the tool to, if you have had a thought of a module where you want to work with gated signals, this is a really good way of accepting all different kinds of gates while also protecting the circuitry on the other side of the OpAmp comparator. So in the next modular in a week episode, I am building a gate inverter module. So taking a gate and inverting that to an inverted gate output. I don't know how useful this will be. We will see that in the next episode, I guess. It's for building rhythms and stuff like that. You'll see in the next episode. So stay tuned for that. I hope you subscribe, and for that bell button so you get a message when that episode comes out. And until the next time, take care. Bye.